Let's get back to something you guys did last year. Ladies and gentlemen, come on. This is the same section. There's the last two bits of information out of it. Last year you guys worked with area of sectors and arc length in the circle chapter. And we always dealt with that in terms of degrees. If you remember, we did central angle over 360 times the circumference for arc length. Remember, arc length is the distance something is going around the circle. So you're working with how far something is moving. You're working for about what is the portion of the circumference as it's going around. Okay? So, Shay, put that away. Oh, I thought you were doing it. I apologize. Sorry. Again, what's going to happen here is we're going to do stuff like this. The arc length is now going to be defined as S, and it's going to be the radius times theta. And now instead of we're working with degrees, we're working with everything in radians. Basically, that's what you guys did last year without knowing you were working in radians when you did arc length. When you left your answers in terms of pi, you were working in radians, you just didn't know it. So for example, we have a circle, radius of 4, a central angle of 40 degrees, and I want to find the arc length. Remember, the arc length is this part here. 4 times theta, which is 40 pi over 180. Remember, you got to switch it from degrees to radians. So when you switch from degrees to radians, you're multiplying by pi and dividing by 180. And then you just have to simplify your fraction. Zeros drop. What's half of 18? What's half of 2? Or excuse me, half of 4? 2. Very good. What's 4 times 2? 8 pi over 9. And there's your arc length. Again, what you're doing is you're working with simplifying of fractions. Okay? If I wanted to find the area of that sector with that same values, the area of the sector in this case, 1/2 the radius squared times theta. Again, it's going to be theta from degrees. We're going to switch it to radians. So it's times 40 pi over 180. What's 4 squared?
16.
What's half of 16? 8. So we get 8 times, well, remember this was 2 over 9. So what's 2 times 8? So you get 16 pi over 9 something squared. Again, all of this is, to be honest with you, is direct substitution from the formula. You're going to be given a degree measure and you're going to be given a radius. Substitute in, find this, the arc length, and then find the area of the sector given that information. Okay? Probably one of the easier things we've done. I hope. All right. Try this one. What's this? Arc length of a sector has a radius of 9 and an angle of 60 degrees. Give me the arc length, which is S, and the area, please. $60 pi over 180. Zeros drop. 6 goes into 18 3 times. 3 goes into 9 3 times. Okay. The area, 1/2 radius squared times 60 pi over 180. So you get 81 times 30 over 180. Put a pi there. Huh? Well, it's not 3 pi. It's pi over 3. 60 pi over 180 is pi over 3. Okay. So when I get to here, again, is that 27? get 9 pi again? Oh, yeah, 9 pi again?
Yeah, why did it become the 60? Did you use the half of the 60?
Yeah.
Well, yeah, you can.
What's 2 times 3 times 4? What's 4 times 2 times 3?
24.
That's
Five.
Same thing. Yeah.
That 1/2 of the 9 is squared is just being multiplied by the 60 pi, not the 180.
Yeah, because then it's all over 180.
I think
So if you just,
Can you work that 81 pi over?
so instead of doing the 60, you can put 40 for half the 80.
Guys, this is just commutative property of multiplication. The order in which I'm multiplying here doesn't matter. Half of 60 is 30. 9 squared is 81. Pi is in the numerator. 180 is below here. 3 goes into 18 6 times. 30. So you get over 6. 6 divided by 3 is 2. Oh, I had it as a 3. That was my fault there. So it's 2. And this is 27 on top. 27 pi over 2. I see what I did. I went so fast. I said that 6 divided by 3 was 3. Sleep math.
Yeah, but the best of us was server efficient.
Yeah. Story of my life. Okay? Like I said, this winds up being a direct substitution problem. It should not be frightening. Okay? Should not be. Now, the other part of this section is when we start talking more and more about things within radians. And what I want to do here is I want to take a couple of minutes.
Oh, swallow
What I want to do here is I want to start talking about how we graph radian angles. And the reason, or the way that we're going to graph radian angles is again going to be based upon how we use that unit circle. And what I want to do here is just kind of, and I know you guys just got all that stuff yesterday, still have that. I want to show you guys a really nice way of remembering how this works. I'm going to plot this, with your help, only dealing with radians. So that means I start here at 0, I go all the way around, and what do I wind up at? 2 pi. Okay? So therefore, what's over here? Pi. What's here? And then what's down here? Everybody okay with that? Let's do it the same way. I think we might have done it like this yesterday. What's half of a half? A fourth. So halfway between pi over 2 and 0 would be pi over 4. Halfway over here would be
Maybe 3 halves pi.
3 halves pi is here. 3/4 pi. Remember, watch this. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4. Okay? What's happening here is every time you're going up by a quarter. 1/4, 1/2, 3/4, 1, 1 1/4, 1 1/2, 1 3/4, 2. It's just going up by 45 degrees each time, pi over 4. It's 1/4 the way around each tick. All right? After that, we talked about the 30 degree. 30 degree in relationship to the 90 degree was how much of it? It was a third of it, so that means we wrote the next one as pi over 6. Remember that? And every time we went up 30 degrees, how much did we go up? A sixth. So this was, now I'm just going to write this in terms of the fraction right now. 2/6, 3/6, 4/6, 5/6, 6/6, 7, 6, 8, 6, 9, 6, 10, 6, 11, 6. All I'm doing is I went all the way around, counting by a 6th, which means there's a bunch of those I can go back and simplify. What's the first one I can simplify?
36.
So what do you get? So I can say that's pi over 3, 2 pi over 3. Now, was it this class that saw a nice pattern here? 6, 4, 3, 3, 4, 6, 6, 4, 3, 3, 4, 6.
Yeah.
You guys remember that? Okay. Well, we had someone last hour point out something else. Pi, pi, pi. Everybody okay? The numerators are all pi. Numerator is 1 less than the denominator. Good. Numerator is 1 more than the denominator. The numerator is 1 less than twice the denominator.
All right, that's good enough.
What's 4 times 2?
8, 2 times 2.
Thank you. 2 times 2 is 4, minus 1 is? 3 times 2 is?
6.
Minus 1 is? 4 times 2 is? Minus 1 is? 6 times 2 is? Minus 1 is? 11. So if you remember, pi, 1 less, 1 more, weird. Your face. Oh.
Technically, our fingers are all individual.
All right, anyway. So what happens here, guys, is I'm trying to help you figure out a way that's going to be easy for you to memorize this. This is something you're going to have to know. You're going to have to know how this works. You're going to have to know where everything goes. You'll have to understand how these things bounce around, especially when we get into 13.2, 13.3, and all of chapter 14 is based upon the knowledge of your quadrants within the unit circle. It is extraordinarily important to know. Okay? So again, let's talk about how do we place then 2/9 on a grid. Where does it go? Let me ask you this. Is it more than a half or less than a half? Less than a half. Is it less than a third or more than a third? Less than a third. So it's about here?
That's half.
What quadrant is that? That's really all you got to be able to do. When you're looking at radians and graphing radians, what you're working on is getting a rough approximate of what quadrant it will be in by seeing if it's more than a half. If it's less than a half, it's first quadrant. If it's between 1 and a half, it's second quadrant. Between 1 and 1 and a half, it's third. Between 1 and a half and 2, it's fourth, and so on and around. Okay, that's what we're looking at being able to do. Let's try another one. (19 pi over 12). I want to graph that. 19 pi over 12.
Quadrant 3.
It's more than 1, but is it more than 1 and a half? Well, let's check. 12 goes into 19 how many times? Once, and how many are left over?
7.
What quadrant would that be? Fourth quadrant. See how this is more than a half?
Oh,
So what happens, this
Yeah.
gets you here,
Yeah, I
this is
thought
another
that-
half, and that's another 12.
Yeah, I thought that the left side was a 3.
I got you. All right, so that gets me over there. Does that make sense? Okay. What happens when it's going the other direction? complicated things, okay? Negative 13 pi over 4. What direction am I going? The other way, clockwise, okay? 4 goes into 13 how many times?
3.
3.
3 and a 4.
So it's negative 3 and a 4, okay? So here's 1 pi, 2 pi, 3 pi, and a quarter. Well, actually, quarter pi would be a half. I don't even have this program if you tell me to update it.
You either.
I think you just confused yourself.
I don't know. I can't remember.
Okay, does that make sense how we're doing that?
Yeah.
All right. Now, let's take this even a step further. Let's say I wanted to go back to 2 pi over 9. And I want to go ahead and not only graph it, I want to talk about 2 pi over 9. I want a positive coterminal and a negative coterminal without changing it to degrees. Now, this is a lot simpler than than you guys believe. Is 2 pi over 9 within one revolution? One full revolution?
Yes, it is.
It is.
Yes.
So, if it was 15 degrees, you'd add 360 and subtract 360, correct? I'm in radians, so instead of adding 360, I'm going to add 2 pi.
2 pi.
But now, since I'm dealing with a fraction, if I want to rewrite 2 pi into a fraction with 9 as a denominator, what would I add it as?
18 pi.
I add 18 pi over 9. So the positive coterminal would be 20 pi over 9. What would the negative be? Very good. Everybody see what we just did? Again,
I saw it.
what we're doing here is just like before. If you're within one revolution to start, you're within 360 degrees. If you're within 360 degrees to start, you're going to add 360, subtract 360. Right now, there's no such thing as a degree. We're in radians. So being within 2 pi, between 0 and 2 pi, is one revolution. 2 pi over 9 is within that parameter, which means all I have to do is add 2 pi to it. Now, I'm not just adding the number 2. Since it's a fraction, I'm going to add the fractional equivalent of 2. 18 over 9. Common denominator and go. Okay? See that now?
Yeah.
Works the same way with the other ones. 19 pi over 2. When we wrote that one out a second ago, we said that was still within one revolution, correct?
Yeah.
Yeah, okay. So 19 pi over 12 means I'm going to add what?
24.
Very good. So I'm going to add 24 pi over 12, because that is one revolution. I'm going to subtract it. Everybody okay with that?
Yeah.
Okay.
Yeah.
Now goes the weird case.
Oh, Mr. Murphy, don't do it to him.
Okay, it's good for you.
It's not.
We said earlier that's more than more than one revolution, correct?
Yeah.
Okay. If that's more than one revolution, we'll make this positive right now so it's a little bit cleaner to see. Let's say it's positive 13 pi over 4. It was.
Okay.
Okay? We'll say we have a positive 13 pi over 4 to start with. We all agree that that's more than one revolution, correct?
Yeah.
Okay. If that's more than one revolution to start with, how many times around is that? 4 goes into 13 how many times? So it's 3 and 1/4 pi. Now, if I write it out like that, to get it within one revolution, what would I have to back out?
Subtract 3.
6 pi?
I'm gonna write it out two different ways. I'm gonna write it out, it was actually 8, but I know you were rewriting this as improperly. Right, because 3, here's 1 pi, 2 pi, 3 pi, so it's over here right now.
Oh.
You were thinking 3 revolutions, okay?
We'll just flip it.
So, let's see. To back it within one revolution, all I have to do is this.
1 and
Now is it within one revolution?
Yeah.
1 1/4 pi? Would that be the positive coterminal then? Yeah. Subtract, yes sir.
It's not the same, can you just subtract 8/4 pi?
Yes.
Okay.
8 pi over 4, but yeah.
Oh, yeah.
Yeah. Yeah, you could do that as well. Some people see it this way better, some people see it the other way. I'm going to show both ways here, okay? What I'm doing here is one method of doing that. We are now within one revolution. There's your positive coterminal. Subtract 2 again. What is that, -3/4 pi?
Yeah.
Okay. What Ryan's talking about here is that if you had started with 13 pi over 4, and you recognize that that's more than one way around the circle, all he's doing is just subtracting this way and saying -8 pi over 4 to get 7 pi over 4, which is your positive. Yes, sir.
Can you just see, like, try subtracting the 2 and see if it's still like a positive and then know that it's
Yeah.
Are you sure
one
that
on
number,
side and all like.
Yeah. No, that's fine. What's up?
wouldn't it be 5 pi over 4, not 7 pi
Yeah.
over 4? Because you
Mr. Murphy, let's just all go to sleep.
Yeah.
Yeah. And then you minus.
Yep. And then you subtract it one more time.
Oh my god.
Relatively straightforward.
Sure. I like it.
If you say so.
I don't think it's that bad.
If I do so,
We'll give you guys a few problems for tonight then.
What do you think is bad?
Yeah.
This?
No, just in general, what do you think's bad in math?
worst math topic.
Yeah.
You'll see it.
I don't want to see it.
Quadrilaterals.
Yeah. No.
Because like everything you say is like, this isn't bad.
I try to break it down into easy terms for you guys.
Yeah, but I want to see something that you think is bad.
All right.
Talking about.
Also, graph.
These are, if you remember from yesterday, those first 4 problems you did were just find positive and negative coterminal. I want you to graph, these are in radians, so I want you to graph 4 radian angles real quick, and then find the positive and negative. Count again, 40, 41, 42, 43. I can count. So damn! And then 60 through 65, which is how many problems, Katie? Very good. And then 80 through 86. All right. I don't think it would take you very long. And it'd be all right. You're gonna get. These are fast. They're easy. These are series of sectors in arc length. Come on, it's a formula. Yes, sir. Hardest one I did in high school. I don't think it was. I was bored. I barely got B's, but I didn't do any work. I'm not lying.
That's where I'm at.
Yes, sir.